So this is an overview of nuclear issues that are particularly appropriate, I hope, for physicians and people who are interested in the International Physicians for the Prevention of Nuclear War. Here are some messages that struck me strongly when I first encountered IPPNW back in 1980 when it was formed. Physicians from both the USSR and the USA joined together to form IPPNW, and this was already a very strong message. It's a human race issue. It's not an issue of what form of government you have or what beliefs you have, what religion you are. It affects everybody. It affects the entire creation. And some of the messages they gave out were, I thought, very, very well chosen because they were very professional. They were based upon their own professional background. The medical profession is helpless to help you after a nuclear war. There won't be any hospitals. There won't be any medication. The doctors and nurses will be either dead or sick with radiation sickness. They're not going to be able to help you. So don't think that there's a cure for nuclear war. Prevention is the only realistic possibility. We have to prevent nuclear war. Otherwise, we're dead. And possessing nuclear weapons itself is an addiction. And you can't just quit an addiction. You know, people always say, oh, well, I can quit anytime. Yeah, right. Just try and quit. And you find out you just can't. It's just a fatal attachment to your addiction. And that means that addicts need help. We really, the countries that don't have nuclear weapons have to play a role in convincing those that do have nuclear weapons that for their own sake, as well as for everybody else's sake, we really have to get rid of all these weapons. And yet, who is going to take the first move? Who is going to actually do it? But it's a very important realization that we all have to help people to understand. Also, the opportunity cost of warfare. You know, war itself is one of the greatest threats to mankind, particularly with these weapons of mass destruction. We are our own worst enemies, and we've got to cut it out. We've got to stop having armies and war as a way of solving problems. It doesn't solve problems. It just creates a host of more problems. But the physicians really were smart to emphasize the benefits. Eliminating smallpox worldwide, for example, was a wonderful achievement. And the cost of that was only 2 days of the arms race, just 2 days of the arms race. Providing clean water worldwide would cost about 3 weeks of the arms race. And that would eliminate most waterborne diseases, which are, legion, and which cost a lot of deaths and illnesses. They won the 1985 Nobel Peace Prize. And If You Love This Planet, the film, the National Film Board film, which I was proud to play a role in, won the Oscar in 1983. If you haven't seen that film, I suggest you take a look at it. That's with Helen Caldicott, who wasn't a member of IPPNW, but who was a member of Physicians for Social Responsibility in the United States. Now, just a little history. In Quebec in 1943, this is in the middle of World War II, Winston Churchill and President Roosevelt and our Prime Minister, Mackenzie King, met in Quebec and signed a secret agreement to cooperate in building the world's first atomic bombs. And this agreement included 3 clauses. One is they wouldn't use it against each other. Second, they wouldn't use it against a third party without unanimous consent. And third, they wouldn't divulge any information about it to anybody else without complete consent. Now, the reason why Canada was involved is because Canada had the only reasonably reliable, available source of uranium. And the reason for that was because back in 1931, there had been a radium mine up in Port Radium, way up in the Northwest Territories on Great Bear Lake. And that ore, throughout the 1930s, it had been shipped down to a little town on Lake Ontario called Port Hope. And there it was refined and sold for medical and non-medical purposes around the world. So wherever there's radium, there's also uranium. And the Allies knew that this was the only place they could get uranium without the Germans knowing about it, because the Germans were in control of Czechoslovakia, where the other uranium had come from earlier. And they were also in charge of Belgium. And Belgium, the Belgian Congo was the other major source of uranium. So the uses of Canadian uranium went into bombs, not only for the first two bombs that were built, the first three bombs that were built, but also for all the bombs that were built during the Cold War period up until 1965. And here's an example, a list of the mills, the uranium mills in Canada, and an indication of which ones of them contributed to nuclear weapons. So the tens of thousands of nuclear weapons that were built in the United States all had a bit of Canadian uranium in them. This is what uranium can do to a city. This is one bomb dropped from one plane, and you can see the devastation it causes. The devastation from a nuclear weapon comes from three sources. One is the blast, which is, you've seen probably pictures of it. It's absolutely terrifying. It flattens buildings for miles around. The other is the fireball. There's a huge fireball which has temperatures hotter than the sun and which set fire to everything that's combustible within a very large radius. So wood, paper, plastic, anything that's combustible will burst into flames. And of course, the third thing is radiation. There's immediate radiation, which is given off by the bomb itself, which is called neutron and gamma radiation. And then there's the lingering radiation from the fallout. In the case of Hiroshima and Nagasaki, they dropped the bomb high up in the air so as not to create a crater. So there's no crater, and as a result of the no crater, there's also far less lingering radioactivity, so that today when you go to Hiroshima, you don't find any evidence of the radioactivity from the bomb. But that radiation, those radioactive materials went all over the world in the stratosphere and are still coming down today. They're still coming down into the environment around the world. And of course, from all the atmospheric bomb tests that have happened in the meantime. Now, this is uranium is the key element in all nuclear fission technology, and that includes nuclear bombs and nuclear reactors. Without uranium, there would not be any nuclear bombs of any description. There wouldn't be any. And similarly, there wouldn't be any nuclear reactors of any description. And it's all based upon a discovery that was made in around Christmas time in 1938 in Berlin, Germany. They found that when a neutron strikes a fissile uranium atom, which is called uranium-235, that atom splits into two smaller atoms, which are called fission products, and which are highly unstable and therefore intensely radioactive. That's the bulk of the radioactive fallout from an atomic bomb, and also the bulk of the radioactive waste from a nuclear reactor are those fission products. And energy is released at this point, and the energy that's released is a million times more powerful than chemical energy. And there's also more neutrons given off, and those more neutrons mean that you can magnify the splitting of uranium atoms. You can multiply it very rapidly and get a huge explosion. So that's what allows for what's called a chain reaction. The only material in nature that will undergo a chain reaction that's naturally found is uranium-235, nothing else. But you can't use uranium-235 directly because it's so scarce. Only 7 atoms out of 1,000 in natural uranium. When you dig uranium out of the ground, 7 atoms out of 1,000 are the chain reacting type of uranium. It's called an isotope, the U-235 isotope. The rest of it, 99.3% of the uranium is non-chain reacting uranium-238. So because the uranium-235 is so scarce, you have to enrich the fuel. That's called uranium enrichment. And when you get it up to about 90% uranium-235, then you have the type of uranium that is used in nuclear bombs. However, it can also be done with uranium that's only about 20%. That's called highly enriched uranium, above 20%. It can be used in bombs, but don't make the mistake of thinking, because they talk about weapons grade uranium, which is like 90%. You don't have to be weapons grade in order to make it weapons usable. So weapons usable material is not the same thing as weapons grade material. Okay, and it's very easy to make such a uranium bomb. It's a simple device. It actually could be built by anybody who knows anything about bomb making. It's not hard. And Little Boy was the first uranium bomb that was dropped on Hiroshima on August 6, 1945, using highly enriched uranium. Fat Man, the plutonium bomb, was dropped on Nagasaki August 9th, 3 days later. Now, why is plutonium there? Well, plutonium is not found in nature. It's a uranium derivative, and it is created in nuclear reactors. All nuclear reactors that are fueled with uranium produce plutonium as a byproduct, and it happens to be a more powerful explosive than U-235, but it's man-made. Now, this is how much plutonium, this is the exact size of the plutonium ball that was used as a nuclear explosive in the Nagasaki bomb. That's how much plutonium you need to destroy a city. So this is very, very dangerous material. Now, it turns out that plutonium requires a somewhat more sophisticated design. You can't use the simple design for a uranium bomb for a plutonium bomb. Plutonium has to use a device called an implosion device. An implosion is more challenging. But the other one, the uranium bomb, is what's called a gun tape bomb, and it's a lot easier. Now, you might be interested to know that the very first reactor that was built in Canada started operation less than a month after the Hiroshima bombing. And the reason why was because we were part of the World War II atomic bomb program. And the plaque, the bronze plaque that used to be at the visitor center, they've taken it down now, says that the reactor went into operation on September 5th, 1945, to produce plutonium for nuclear weapons. The reactor was designed by a team of Canadian, British, and French scientists who worked in a secret laboratory in Montreal, just a few blocks from where I live right now, up on the slopes of Mount Royal. And it was intended to lay the groundwork for a more powerful reactor called the NRX reactor. That NRX reactor also produced plutonium. And by the way, it was copied by Israel, and that's where Israel got its atomic bombs, from a copy of the Chalk River reactor. And also, we gave a copy of that reactor to India as a peace offering, as a gift. And India used that reactor to produce the plutonium for their first atomic bomb in 1974. So Canada also helped the British to design the first plutonium that the British got came from Chalk River, Canada, Chalk River, Ontario, from our reactor, from the NRX reactor. So the NRX reactor actually played a role in the American, the British, the Israeli, and the Indian nuclear weapons programs, and even in the Russian nuclear weapons program, because we had a couple of spies in Canada. It turns out that the very day after this reactor started operation, a Russian, a Soviet cipher clerk working in Ottawa defected and revealed the existence of an extensive Russian spy network in Canada, sending nuclear secrets to Russia. And Russia got its first tiny, tiny little speck of plutonium from Chalk River as a result of that. So we played a role in all but the Chinese nuclear weapons program and the North Korean nuclear weapons program. And so we played a role in all the other weapons programs. Interesting, the fact that most Canadians don't know. Now, here's how plutonium is created. Remember, I told you that uranium-238 is non-chain reacting. However, when a neutron hits a U-238 atom, it actually changes into a plutonium-239 atom. It undergoes a change, and it becomes slightly heavier. That's why the number is 239. The neutron gives it that extra weight, that extra mass. But that plutonium-239 is an excellent nuclear bomb material. And in fact, highly enriched uranium and plutonium are the only, even today, those are the only nuclear explosives that are used worldwide. Now, this is how you handle plutonium. Plutonium, although it's highly, highly toxic and radiotoxic, nevertheless, it doesn't give off penetrating radiation. We're going to talk about that in a little while. Consequently, it can be handled safely in a glove box as long as the material is not allowed to escape into the atmosphere outside, because once it's inside the body, it's extremely toxic. But outside the body, it's basically harmless. Plutonium is like that. Now, another thing is that the H bombs, the so-called fusion bombs that are much more powerful than the atomic bombs that are based only on nuclear fission. Is everybody familiar with the difference between fission and fusion? Fission is where heavy atoms are broken apart and release energy. Fusion is where light atoms like hydrogen are smashed together into heavier atoms and produce energy that way. That's called fusion. That's what happens in the stars, in our own sun, for example. Well, the fusion reaction is even more powerful than the fission reaction. But in order to get a fusion reaction going, you have to raise the temperature to 100 million degrees Celsius. And that's done by using a small plutonium bomb at the top. And that small plutonium bomb raises the temperature and ignites the fusion reaction, which then leads to a much more powerful explosion. Howard Moreland was a journalist who wrote an article called The Secret of the H-Bomb. And he's holding a model of the H-bomb to see, so you can see where the plutonium ball is. When they talk about dismantling nuclear warheads, what they do is they simply take that plutonium out of the warhead, and it's no longer a bomb. It's no longer a nuclear bomb. It can't possibly go off without the plutonium. Now, if you take a look at Hiroshima with 15,000 tons of TNT, that's 15 kilotons. A large modern nuclear weapon is much more powerful than that. 15 million megatons of TNT. And you can see the comparison there. So they don't make bombs as small as the Hiroshima bomb anymore. All the bombs are at least 15 times more powerful. And so a strategic nuclear bomb is approximately 1,000 times larger than the Hiroshima bomb. This 15 megaton nuclear test in the South Pacific has a cloud height of 12 miles and a cloud diameter of 60 miles. Just astounding, you know. Now, this chart, I happen to like this chart. That little white dot in the middle represents all of the explosive power in World War II, all of the explosive power in World War II, including the 2 atomic bombs that were dropped on Hiroshima and Nagasaki. All those other dots represent the explosive power of all the nuclear weapons in the world today. So you can just see we have astonishing degrees of overkill. And the ones in red there are the ones which are on fast alert, high alert. It's called high alert. They can be launched within 15 minutes. And once they're launched, these missiles, these intercontinental ballistic missiles, once they're launched, they cannot be called back by any means. There's no way of calling them back. And the US president, for example, would have he'd get briefed for about 30 seconds, and then he would have 12 minutes to decide whether or not to launch a nuclear weapon. So this is a very, IPPNW and many others have been urging the nations to take these weapons off high alert so they cannot be launched so quickly. But it just shows you the madness of the MAD doctrine. You know, MAD stands for mutually assured destruction. So the idea is that if it's mutually assured destruction, nobody will dare to do anything because they know that they too would be obliterated. However, when you get many players involved, when you have North Korea and when you have India and Pakistan, and when you get many players, and also when you maybe even have terrorist groups that could have their own nuclear weapons, then it becomes anybody's guess as to whether this is in any way stability or offers any kind of security. So exploding a 300 kiloton weapon, that's a relatively small one, forms a fireball 2.5 kilometers in diameter. The temperatures at the center of the fireball will be 4 times hotter than at the center of the sun. The heat from the fireball would ignite fires over an area of 105 to 170 square kilometers. So an inferno, as well as a flattening of the buildings through the blast. Here's a comparison to the little dot, the second dot, the complete dot, is all the explosives in World War II. If you go to the left, you see 1/2 of the World War II explosives is the size of the India-Pakistan war that one could imagine taking place with a couple of dozen bombs on each side, a couple of dozen nuclear bombs on each side. In that case, you could have as many as 100 Hiroshima-sized bombs entering into an India-Pakistan war, both of which have their own arsenals. If you go to the red dot, that's the ones that are on high alert. And if you go to the blue dot, that's the one that that represents the total firepower of the US and Russian arsenals. Just astonishing. So what are high alert nuclear weapons? As I said, they're missiles with nuclear warheads that can be launched in 2 to 15 minutes. They cannot be recalled and require about 30 minutes or less to reach their targets. Approximately 900 each US and Russian land-based intercontinental ballistic missiles with 1,900 warheads because they have multiply targeted independent warheads. There's enough here to destroy every city in the Northern Hemisphere, many times over, actually. Approximately 130 submarine-based ballistic missiles with 670 warheads. Those are also considered high alert. So the dangers of launch on warning is the US president, as I said, is given 30-second briefing. A false warning believed to be a real attack would lead to an accidental nuclear war. And there have been many instances of very, very close calls, which are documented by IPPNW, among others. False warning could be due to human error, technical glitch, or terrorist sabotage. So there's also global implications. In addition to the blast and the fireball and the radiation lingering, there's a global implications due to catastrophic climate consequences of a nuclear conflict. Using the same models, the same mathematical models that are used to study climate change today and to study how the temperatures are going up, they find that less than 1% of the global nuclear arsenal detonated in large cities will cause catastrophic disruptions of the global climate, massive destruction of the ozone layer. And due to these climatic consequences, a large nuclear war, even a preemptive strike, that means even if one side gets away with bombing the other side and not getting retaliated against, it'll make the earth uninhabitable for humans anyway. So this is not a war, this is suicide. This is you can't win a nuclear war. And both the superpowers have all, most recently, a couple of years ago, the US and Russia both said simultaneously that a nuclear war cannot be won and must not be fought. Nevertheless, you got the weapons, they're probably going to be used sometime. The only way, as IPPNW says, there's no cure, there's only prevention. And prevention means elimination. You have to eliminate the risk. And eliminating the risk, it's like eliminating the cancer from body. You can't just remove 90% of it. You got to remove all the cancer because it's just going to come back, right? And that's what we have to do with nuclear weapons. We have to eliminate it all. We have a non-proliferation treaty. We have other treaties which say that that's what they're going to do, but they don't do it. And this is why we talk about the addiction. It's an addiction. They can't do it. They need a lot of help to get it done. And that means the people of the earth and the countries of the nations of the earth have to get together and gang up on these superpowers and the other ones who are aspiring to become mini superpowers. And we've got to eliminate nuclear weapons altogether. Either that, or we're going to eliminate ourselves. So how does nuclear war cause climate change? The nuclear detonations in cities cause an immense mass fires, and millions of tons of smoke rises and remains in the stratosphere for years. Once it gets up into the highest stratosphere, it doesn't settle out for a long time. This blocks the incoming sunlight and acts to destroy the protective ozone layer. Nuclear darkness results for years and there's a rapid drop in global surface temperatures. Prolonged cold leads to significant drops in precipitation. Vegetation dies, animals starve, and evolution is set back 4 billion years. 100 Hiroshima-sized weapons, even a small nuclear war, an India-Pakistan nuclear war involving only 100 Hiroshima-sized weapons, that's 0.05% of the US-Russian weapons, would cause 5 million tons of smoke, or could, depending upon the targeting. It rises 50 kilometers above the cloud level into the stratosphere. The global temperatures would drop to little ice age levels, significant reduction in precipitation. This would cause a lot of, as the smoke spreads throughout the northern hemisphere, the whole northern hemisphere would be affected with inability to grow crops. And the temperatures would drop. And this is called the black carbon absorption optical depth. And the days are going on there, June 5th, June 6th, June 7th. It's just day after day showing how the smoke spreads. And we get down to temperatures that are 1.5, as much as 1.5 degrees below. When we talk about a 2-degree rise in temperature, well, 1.5 degree drop in temperature is extremely dramatic. Now, here's what happens finally as a result of an India-Pakistan war. You notice those numbers. They represent, for example, up in the north, we have minus 2.5. In some places, we have minus 1.5. These temperature drops down below here, we have minus 3. So you can see these temperature drops are really quite catastrophic. And that's only for a limited nuclear war. If we talk, here's how it would affect Canadian wheat growing. About a 1 degree centigrade drop would lead to the smaller region of wheat crops, and a 2 degree centigrade drop would lead to a much, much smaller region of food crops. If we had a large nuclear war, a high alert strategic nuclear war, using only the weapons on high alert, then we would have a more catastrophic situation because the temperatures would drop all the more. And it would be 12 degrees, 20 degrees, 15 degrees less drop of temperature. Here we have a graph, but you can see that even the small nuclear war is the red line. That gives you a regional nuclear war, the drop in temperature. The green line gives you the high alert war, and the mauve line gives you the war that would result from all the nuclear weapons. So these are factual things which can be used to convince people who are worried about climate change that, we're worried about climate change with good reason, but we're talking about decades. This could happen in a matter of hours. I'd now like to turn to radiation levels on the human body. When you go down to the bottom of this list, you see where you get really deadly doses of radiation, and that happened to an awful lot of people. About 200,000 people were killed in the Hiroshima bomb. Most of that was due to blast and heat. Some of it was due to prompt radiation from the neutrons and gamma rays. And 1,000 rem, which is the same as 10 sieverts. Here in Canada, we use the unit of sieverts, which is 100 times less in size than the dose in rems. So 10 sieverts is the same as 1,000 rems. And if you look at the line right second from the bottom, 4 sieverts, 4 to 10 sieverts will kill people. About 60 to 95% of the people will die in 30 days. But as you go back up to the top, 5 to 20 rems, which would be, again, 0.05 to 0.2, to 0.02, to 0.2 sieverts, would give you possible late effects, possible chromosomal damage. So now you might be surprised to know that even back in 1931, this is a document from the Canadian Department of Mines in 1931, and it says precautions for workers in the treatment of radium ores. Remember I told you there's that radium ore up in the Great Bear Lake area? It says lung cancer, bone necrosis, and rapid anemia are possible diseases due to the deposit of radioactive substances in the cell tissue or bone structure of the body. We're talking here about internal ingestion of radioactive materials. And that's the main concern when we talk about long-term, low-level radiation exposure. It's mostly through ingesting, drinking, inhaling, or otherwise getting these radioactive materials into your body. And there they can lodge and build up, and that can cause a lot of harm. Henri Becquerel discovered radioactivity in 1896. He discovered that uranium and thorium ores are both radioactive. And what that means is it gives off an energy that will expose a photographic plate, even if the photographic plate is wrapped in dark black paper. And here's a picture of a lump of uranium ore in a cloud chamber, a device where you can see the visible tracks left by the emissions, which are alpha, beta, and gamma particles given off by this uranium ore. You can see it. Normally, we can't see, feel, or hear, or smell. It's invisible to our five senses, radiation. We have no protection against it for that reason. But here you can see the energy just pouring off this rock. And the amazing thing is that energy is pouring off that rock 7 days a week, 365 days a year, and it's been pouring off like that for over hundreds of millions of years. The half-life of uranium is 4.5 billion years, which means this rock is emitting that energy, that radioactive energy, all the time. And this makes a big difference between, say, an X-ray machine. An X-ray machine gives off radiation, yes, but when you turn it off, it stops. There is no danger once it's turned off. Nobody knows how to turn off radioactivity. It just continues and continues and continues. We can't slow it down. We can't speed it up. We can't stop it. Now, what happens here is that the energy is coming right from the nucleus of the atom. It's called nuclear energy for that reason. It doesn't involve the electrons that circle around the outside. The circling electrons are what give you the chemical energy. But the nuclear energy is much more powerful. It's the strongest force in the universe. The smallest object in the universe, which is the nucleus of an atom, has the strongest force in the universe. Isn't that amazing? And what was pointed out by the early scientists was that if you add up all the energy that's given off by this uranium rock, if you add it up for a couple of 100 million years, you will see that you have enough energy to destroy the Earth. But it's given off so gradually that it can't do that. And we can't speed it up or slow it down. So there needs to be a trigger. And there was no trigger by which we could do it until we discovered the neutron. When the neutron was discovered, then things started clicking. Now, the emissions from the nucleus are gamma rays, which are photons, like X-rays, but more powerful. But it also gives off particles, which have much less penetrating power. The alpha particle goes only a few microns, and the beta particle goes only a few centimeters. These are electrically charged particles which cause ionization. And you know what that means is breaking molecules into fragments which are electrically charged. Those are called ions. Sometimes they're called free radicals. Alpha particles can be stopped by a sheet of paper. They're harmless outside the body, but exceedingly dangerous when ingested or inhaled. In fact, an alpha particle is about 18,000 times more damaging than a beta particle from a tritium atom. Beta particles penetrate only partway. They can damage the eyes or skin externally, but the main danger is internal exposure. When they get inside the body, that's when they do the real damage. Gamma rays are highly penetrating. They give whole body radiation, and heavy shielding is often needed. But when we talk about chronic low-dose exposure, any one of these can lead to cancer. Now, here are the tracks made by a particle, a speck of plutonium inside lung tissue seen through a microscope. This is over a 48-hour time period. The lung tissue is the lung of an experimental ape who was sacrificed for this. The cells close to the source may be damaged, yet able to reproduce, causing lung cancer many years later. So the cells that are damaged, the DNA molecules are damaged, they can develop into cancer cells later on. Also, reproductive cells like sperm and eggs can give rise to genetic abnormalities in the children, grandchildren, great-grandchildren of people. It's passed on from generation to generation, that genetic damage. Now, Marie Curie in 1898, 2 years after Becquerel discovered radioactivity, she's an excellent chemist. And so she she crushed the uranium rock, the uranium ore, and separated out chemically the uranium. And she found that the uranium was indeed radioactive, but the rock, the crushed rock, is much more radioactive than the uranium. This made her realize that there are more radioactive materials there. And she discovered two of them, radium and polonium. They are two of the so-called decay products of uranium. It turns out that when a uranium atom disintegrates and gives off those emissions, it also changes into a new atom. And eventually it becomes radium, and eventually the radium becomes polonium. By the 1920s, they realized that these young girls who were hired to paint dials of watches and instruments with radium-based paint to make them glow in the dark, that they ingested minute amounts of radium when they licked the tips of their brushes to get a very fine point to do their very great detail work. And they had deaths from fatal anemia, bone cancer, and head cancer. The fatal anemias, radium goes to the bones and teeth. The dial painters developed severe dental damage called radium jaw. Radium also damaged blood-forming organs in their bone marrow and caused rapid anemia, as did Marie Curie and her daughter Irene. And others developed an epidemic of bone cancer. And radon gas produced by the radium was carried by the blood to the head, and that caused head cancers, cancers of the sinus and mastoid cavities in the head. So we knew very early on, by the 1920s, we knew just how deadly radium could be. And for that reason, that's why in 1931, we knew that this is very dangerous material, radium. Also, it was discovered by the 1930s, it was clear that radioactive radon gas is produced when radium atoms disintegrate. It's the leading cause of lung cancer among non-smokers today. And it causes lung cancer and other lung diseases in not only uranium miners, but lots of other underground miners. And it's killed countless thousands of underground miners over the centuries. Radon gas deposits solid radioactive materials in lung tissue. It's 7 times heavier than air and travels great distances. Although radon is a gas, its products are solids and lodge in the lungs. And you will notice that there are 1, 2, 3, 4, 5, 6, 7 radioactive byproducts of radon, and 3 of them are polonium isotopes. And those polonium isotopes contribute 85% of the damage to the lung dose. It's from alpha-emitting polonium. These are, by the way, radon, uranium, radium, and polonium are all alpha-emitting materials, and they are among the most deadly of the radioactive materials. Here we have Alexander Litvinenko, who was killed by another alpha-emitting material. I don't know if you remember the name. He was an ex-KGB agent who was murdered in London by a very small amount of polonium-210 being poured into his tea. It's chemically similar to potassium. It attaches itself to the red blood corpuscles. It travels through the body, damaging the soft organs. It's 250 billion times more toxic than hydrogen cyanide. It's the only material that can deliver a dose of whole body alpha radiation. It's produced by the disintegration of radon atoms. And it's probably the cause, according to the American Health Physics Society, it's probably the cause of up to 90% of the deaths that are attributed to tobacco, lung cancers, heart attacks, and strokes. And that's because when you harvest the tobacco plant, you also harvest polonium-210 in the tobacco, which arrives in the tobacco leaves as a result of radioactive fertilizer that's used on the crops. Weight by weight, according to Los Alamos National Laboratory, it's about 250 billion times as toxic as hydrogen cyanide. Now, here is a wall of uranium mining waste. When you mine uranium, you take away the uranium from the ore, but all of the rest of it which it contains all of the radium, all the radon, all the polonium, all the radioactive byproducts of uranium, are left behind in the sandy residues. And Canada now has approximately 230 million tons of these sand-like residues. This particular wall is 30 feet high, and that's 10 meters. And behind it is a lake, a veritable lake of the same radioactive sandy material, which is left over from uranium mining in the Elliott Lake region. So this is a real problem. By the way, the half-life, the effective half-life of these radioactive sands are about 76,000 years. That's how long it'll take for just half the radioactivity to diminish. Now, everything changed in 1938 to 39, as I said earlier, when we discovered nuclear fission. A neutron strikes a uranium atom. The uranium atom splits into two highly radioactive fission products, releasing energy in the process and releasing more neutrons. Well, some of those extra neutrons go on to create other radioactive materials. Now, here's a CANDU fuel bundle. It's about the size of a fireplace log. It can be handled safely before it is used, but after use, the gamma radiation alone will kill any human being in less than a minute. This is an ad from the nuclear industry. It's called Small Wonder. It's saying, isn't it great how much energy there is in this fuel pellet, this uranium fuel pellet, which is a simulated one that he's holding in his fingers. He's an actor, of course. Well, what he doesn't say is that, yeah, that's great, all right. It gives you as much energy as a carload of coal. It's true. And it also doesn't release carbon dioxide into the atmosphere when it's used that way. But you have to keep an eye on it for the next 7 million years. You can't throw it away. And the reason why is after it's used, it has become one of the deadliest objects on Earth. It's high-level radioactive waste, and it's going to remain dangerous for a long, long time. So here's how a CANDU nuclear reactor works. We put the uranium into the reactor core, which is that yellow area, and we pump a lot of water through it. And what the reactor core does is it fissions the uranium, releasing a lot of energy in the form of heat. That heat is used to boil enormous amounts of water, and the water goes to the steam generator, where steam is generated and turns a turbine to produce electricity. So basically, nuclear power is another way of boiling water. Anything that will boil water will allow you to generate electricity. They can do it with oil, they can do it with gas, they can do it with coal. But of course, in that case, you're releasing carbon dioxide. In this case, you would not be releasing carbon dioxide, and that's one of the good things about it. However, it does produce radioactive waste, which remains dangerous for 10 million years. So that's not so good. Here's a fuel bundle. A freshly removed fuel bundle from a nuclear reactor will give a lethal dose of radiation in 20 seconds to a person standing 1 meter away from it. That's based on that chart I showed you earlier. The kind of radiation doses that killed humans in Hiroshima, 100% of them exposed to those high doses, that would happen for just one of these fuel bundles. And of course, there's about 3 or 4 million of them so far. Now, meanwhile, this fuel bundle looks solid, but radioactive materials are contained inside. So the fuel bundle is actually the container for the fuel, for the radioactive poisons that can leak out through tiny pinholes and cracks. Severe fuel damage causes massive leaks. Fuel suffers corrosion, distortion, and embrittlement in the reactor, and it continues to degrade once it's out of the reactor. For the first 10 years, they have to put the used fuel into a deep pool of water, slowly circulating water, to keep it from overheating spontaneously, because it's still giving off so much radioactivity that it will spontaneously boil the water if it's not circulating. You have to remove that heat. As a matter of fact, at Fukushima, for example, when the reactors were shut down, it was the heat from the radioactive poisons that caused the meltdown of those 3 reactors. The heat alone is enough to melt the core of a reactor. And when you bury it underground, the rocks are heated up even if it's 70 years after it came out of the reactor, when you bury it underground, it'll heat up the rocks underground for approximately 50,000 years. And after 50,000 years, it'll return to more or less normal temperatures. But that's nothing compared to the 70 million years, or sorry, 7 million years that the waste remains dangerous. Now, here are a list of all the radioactive materials that are created inside the reactor. Not all of them, but many of them, 211 of them. And you will notice that most of them are very normal elements: sulfur, chlorine, potassium, manganese, iron, cobalt. These are not radioactive materials in nature. They're not radioactive. But in the reactor, these become radioactive variations of non-radioactive materials around us. And that's the danger, because these radioactive varieties, they're like evil twins of the non-radioactive materials in our environment. Once you mix the radioactive variety with the non-radioactive variety, you can no longer separate them. And consequently, it all becomes, in a sense, radioactive. And that's why we want to keep this stuff out of the human environment for forever, basically. Now, as you can see, this list goes on and on. There's the plutonium isotopes, by the way, that are created. Notice there's a whole bunch of isotopes of plutonium, but all of them are chain reacting. All isotopes of plutonium are chain reacting. That means that no matter what the mixture of isotopes is, you can always use plutonium for nuclear weapons. That's not true with uranium. If uranium has too much U-238, you can't use it for a nuclear weapon, but plutonium is good all the time. So this list of 211 is by no means complete. Now, I'm looking at my time. It's already almost an hour. Let me just continue. Shall I stop, or shall I continue a bit more?
Maybe let's see if we have any questions at this point, and then if we have a little time after, continue more, if that's okay with you.
Yeah, that's
Dr.
okay. I'll
Ford.
just go through these 4 little slides and then we'll have questions, okay? Each one of these radioactive materials has its own pathway through the environment and through the human body. For example, iodine-131 is a radioactive form of non-radioactive iodine. It goes to the thyroid gland in the throat and damages it. 6,000 children had to have their thyroid glands surgically removed in Belarus because of the iodine-131 from the Chernobyl accident. Cesium-137 goes to the soft tissues, the meaty tissues, and that's what causes meat to be unusable, unfit for human consumption. For 20 years after Chernobyl, sheep farmers in northern England and Wales could not sell their sheep meat because of cesium contamination. And even today, when hunters kill wild boars in Germany and Bavaria and other places, they can't eat the meat because it's too radioactive. Strontium-90 goes to the bones, the teeth, and mother's milk. It causes bone cancer. And I'm just giving you an example of how complicated it is to keep track of all these radioactive materials.